Welcome to part 2 of the Ask Peter video that answers Aidan's question, why doesn't the chocolate in chocolate chip cookies melt when they're cooking the cookies? Again, thanks very much to Aidan for this very clever question. Actually, children of today are really smart. Just look at Aidan's cousin Jake learning the clarinet in Brisbane. And there's Lila in the background. It's very good that children of today are so very, very clever. I'm talking about you, because the answer to Aidan's clever question is very difficult, but I think you're clever enough to understand it if you pay attention and listen closely. In part 1, I performed a series of experiments, cooking experiments, and these showed that normal eating chocolate and cooking chocolate doesn't flow when heated inside a chocolate chip cookie. In fact, the dough doesn't restrain the chocolate and doesn't stop it from flowing out. We investigated that further by putting the chocolate chips on a plate. And when you make the chocolate sort of stick proud of the cookie, it didn't flow either. It didn't cover the cookie when we put it in the oven. Really very extraordinary. And then heating the cookies for half an hour, just in case 10 minutes at 180 degrees C wasn't enough to melt the chocolate. That also didn't cause the chocolate to flow. Nothing that I could do in that oven would make the chocolate flow. It would get slightly soft, but it wouldn't melt as you'd expect, as ice does. So I read up chocolate on the internet, and this is what I found. I found that all the ideas so far were based on the assumption that chocolate behaves like a normal material when you melt it. It turns out this was a wrong assumption. Let's look at normal liquids first, and then we look at abnormal liquids like molten chocolate. Scientists call normal liquids Newtonian fluids. That's because nearly 300 years ago, Sir Isaac Newton investigated how liquids flow with experiment and with maths. He discovered how liquids flow in terms of viscosity. Viscosity is like thickness or stickiness. Syrup or honey is much more viscous than water. Water is less viscous, it flows easier. Simplistically, Newton's law says that fluid flow depends on two things. It depends on the pressure of the fluid and it depends on the viscosity of the fluid. Let's consider the pressure first. That's the easier one. We increase the pressure, the fluid flow velocity increases. Now this is quite easy to illustrate. I've got a plastic bottle here and it's got a little hole at the bottom that's covered with sealed with some tape. And inside the bottle I've got some water that I've put some food coloring in to make it easier to see. When I pull the tape off, we should get a nice jet of colored water. Let's have a look at that, caused by the pressure of the water above the hole. Okay, now I can increase the pressure on the water at the jet by blowing into the bottle quite easily. Watch this. That's not bad, hey? Now, as I increase the pressure, the velocity increased, the jet went further. Now, there's another way of increasing the pressure on the jet, on the water in the jet, and that is to take advantage of gravity and put more fluid in, put more water in. Watch, look, the jet should be going further. It's not as dramatic as when I blow, but you can still see the effect. There you are. What do you think of that? But I say blowing is much better, eh? Secondly, Newton said that the flow of a fluid depends on viscosity. Viscosity may be Maybe sounds a little bit difficult, but actually, if you remember where viscosity comes from, it's much easier to understand. Viscosity comes from the Latin word viscum, which means mistletoe. You know the plant that grows on trees is a parasitic plant. Well, another thing about mistletoe, besides that you can kiss someone who's standing underneath mistletoe, the other thing about mistletoe, the plant, is the berries can be used to make a very, very sticky glue. This glue is called viscum. In fact, people used to catch birds, they still catch birds, by putting a glue made out of the viscum berry, out of the mistletoe berry. They put this glue on twigs, birds land on it, and they can't fly away. So it makes sense that a fluid that doesn't flow very easily, a fluid that's a bit sticky or stiff, like honey, is said to be very viscous, or it has a high viscosity. It has a high resistance to flow. Water has a low viscosity. It can flow easily. Honey has a high viscosity. It doesn't flow very fast, doesn't flow very well. Cheers. Water is a good example, as you said, of Newtonian fluid. When ice, the solid form of water, melts, the resultant water flows away. The gravity on just a tiny bit of water causes it to move out of the way. Water doesn't stand up in lumps, does it? Other examples of Newtonian fluid are turpentine, methylated spirits, brake fluid, lubricating oil, petrol. All of these Newtonian fluids are typically simple compounds. They behave in a uniform, simple way. Maybe for simplicity, Newton only worked on these simple fluids, what we now call Newtonian fluids. Newtonian fluids have a constant viscosity. The flow of these Newtonian fluids do not vary with applied force, nor does it vary with time. The viscosity may vary with temperature. If you heat it up, they often get a little bit thinner. We expect this kind of behavior. Imagine if you pressed on water and it became thinner, or if you pressed on water and it became thick, like peanut butter. It doesn't do that. Well, what about non-uniform liquids? What about liquids with bubbles, or liquids with crystals, or other mixtures of liquids? These behave very differently from simple fluids. These non-uniform liquids are called non-Newtonian fluids. In non-Newtonian fluids, their viscosity, their stiffness, varies in many ways. The viscosity can vary with history, like lava. In molten lava, the viscosity varies according to how quickly it cooled down from the extremely high temperatures underground, deep in the earth, to the cooler but still very hot temperatures on the surface of the earth. If they cool down slowly, bigger crystals can form, which will make it more viscous, more stiff. It will be less flexible. If gases are able to come out as bubbles, that also is going to affect the lava's viscosity. Then there are materials where the viscosity increases with time. A lot of printer ink becomes more viscous if you leave it alone for some time. Then there are even other materials, there are other liquids, where the viscosity decreases with time, like yogurt and peanut butter. Then there is some strange materials where the viscosity increases with pressure as you increase the pressure. Cornstarch is a good example of that. And let me tell you something really exciting. Robert, who's Joel, who lives in Bristol, it's his grandfather. Robert has made a really interesting YouTube on cornstarch. That's in part 4 of this Ask Peter. Now we start getting towards chocolate. There's some liquids where the viscosity decreases with pressure. Tomato sauce is one. You all know how difficult it is to pour tomato sauce. If you take the lid off and tilt it, the tomato sauce doesn't flow, or it flows only when you have a lot of pressure. Or maybe you've got to go like that, and then boy, the tomato sauce comes shooting out, and you might get it all over your fish and chips and over your shirt. Who knows, you might get into trouble. Toothpaste is another one, another non-Newtonian fluid, where the toothpaste doesn't come out of it the weight of its own gravity. It will come out, though, if you squeeze it, and you don't even have to squeeze it very hard. And its viscosity decreases with pressure. Another one is mayonnaise, and here's one that you all know very well, various cosmetic creams. This is Vaseline, doesn't flow at all, and yet it looks quite stiff. But if you put it on you, and if you apply enough force, it's very easy to move. Look at that, it's gone very, very, very thin. It's not viscous at all, if you put enough pressure on it, and not very much. And then the one you've all been waiting for, chocolate. Well, chocolate is a mixture of particles, sugar particles, cocoa solids, and milk powder in a base of cocoa butter. When you melt the chocolate, the cocoa butter becomes liquid fat, but all the particles of cocoa solids and sugar and that lock together in this liquid fat, and they make it very viscous, so it doesn't flow. If you apply enough pressure to some molten chocolate, then the particles can slip against each other, and the lock, as it were, is broken, and the chocolate can flow. So in summary, water is a Newtonian fluid. Water flows even under very, very, very small pressure. Just the weight of a drop of water is enough to make it flow. We don't get water sticking up like a blob of ice. We do get surface tension. You can get a sort of a bubble of water on a plate or something. That's a different issue. With molten chocolate, it's a non-Newtonian fluid. If you heat it, it melts, but a small amount of chocolate won't flow, molten chocolate won't flow under the force of gravity, under its own weight. To make molten chocolate flow, you must apply force. You must stir it, or you must press it with your finger. Then it will flow. To check what this means, I went back to the oven. I got a plate and I put some chocolate chips on the plate again. I was getting quite good at doing this by now. And I also got some ice, and I broke the ice up into small pieces about the same size as the chocolate chips. And I put that on the plate next to the chocolate chips. Then I put the plate inside the oven at 180 degrees C for 10 minutes. The same conditions that we used to cook the chocolate chip cookies in the beginning. But after 2 minutes, the ice had melted already, so I took it out of the oven. The ice had gone, and there was just a thin, uniform, flat film of water on the plate, together with the chocolate chips. But this is to be expected. We know that water is a Newtonian fluid, and it flows it's subject to a constant viscosity, and it will flow under its own weight, and it will cover the plate, and you won't have bits of water sticking up. But the heated chocolate behaved very differently. The chocolate chips did not flow. We know that's because that's a non-Newtonian fluid with a very high viscosity. That is, the chocolate is stiff, so it doesn't flow under the weight of the small chocolate chips. I'll tell you a little secret. Since all the tests I thought were now finished, because I thought we found out why chocolate doesn't flow in the chocolate chip cookies when you cook them, because I thought all the tests were finished and I thought nobody was watching, I looked around. I thought I would just eat the chocolate chips that were left. But I hadn't been thinking about what we've learned, because when I tried to pick up this molten chocolate chips with my fingers, I found I couldn't. the chocolate just turned to butter, just turned to nothing. And it just made a grease mark on the plate. That's because I wasn't thinking. The viscosity of the molten chocolate is very high if there's no force on it, so it stands up. It resists the force of gravity. But as soon as I tried to pick it up with my hand and squeeze it with my fingers, that just made the viscosity collapse and made it go very low, and the chocolate became very runny, and it just smeared the plate, so I couldn't pick the chocolate up. Instead, I had to lick my fingers. So I had the chocolate anyway. I thought I deserved it. Well, I hope that now you know why the chocolate doesn't flow and run away in chocolate chip cookies when they're heated during manufacture. Thank you very much for watching this. I hope you enjoyed it as much as I did. I hope you learnt as much as I did. And thank you and goodbye to Aidan and Liam, to Josh, Rachel and Elijah, to Jake and Lila, and to Joel and Mika. Bye all.